Θα μιλήσω στα αγγλικά, γιατί έχουμε τους προσκεκλημένους μας. So I thank the organizing committee for giving me this opportunity to present you the project Offshore Wind. Offshore Wind is a project that is one of the activities of the Energy Competence Center that was launched by the National Technical University in collaboration with its Institute of Communication and Computer Systems, and brought together a number of entities, not only from the research area, but also from the private and the public sector. On this slide, you see the partners of this Energy Competence Center, and going to start saying a few words about Offshore Wind. Offshore Wind, as I said, is one of the center's project, and it focuses on offshore wind energy, and particularly on floating systems. In this project, partners, which are also partners of the center, are Hydros Engineering from the private sector with experience in maritime engineering, the National Observatory of Athens, which we all know, which has to do with the wind and wave climate, the University of Western Macedonia and the National Technical University of Athens from the academia. Now, this project was partially funded by the General Secretary of Research and Innovation. In the next slide, I'm going to show you the big picture of what we're doing. In few words, what we try to do is to bring up a bundle of services or solutions based on our research expertise and our long-lasting know-how built up through research and development projects funded either by in a national or in a European context. What you see here are the four pillars of what we expand our services and solution. The first is the wind and wave, the resource, clearly, it's number one, where we are providing the information at a very high resolution level, both regarding the meteorological aspect and the microsighting, which has to do with any effect the nearby topography may provide. Then we have the wind park design, where we aim at having the minimum LCOE, and this has to do with the layout of the park, the coupling, noise, and also the operation control for minimum weight shading, which is one of the things that may affect the operation of a wind farm. Then the finance, and not only, together with socioeconomic analysis. And the last pillar is detailed engineering, which goes through all of the stages that are needed in order to come up with a well-defined wind turbine system. In the next few slides, I have selected three topics, which gives you some of the highlights of what we're doing. The first has to do with the redesign of the Horns Reef 1 wind park, where we aimed at lowering the LCOE and where we applied all of the software and the computations that we have developed and we have integrated in this bundle of services. The second has to do with the floater design tool, and it's related to the benchmarking in extreme wave conditions. The third has to do with the formulation, the application of high-fidelity aeroelastic modeling beyond the state of the art, where we are applying large eddy simulations, CFD simulations, together with the aeroelastic behavior of the wind turbines. Let's start with the first one. What you see on this slide is the original layout of the Horns Reef Park, and on the right-hand side, you see the optimal layout that we came up with. The positioning of the turbines is different, and also the cabling connections. What we achieved is shown here, and it is shown in the last column, where with arrows we show the benefits. The benefits you see that without making any other except of design modifications, we were able to decrease the LCOE and also have what is here of importance. We have reduced by a considerable amount the cable cost as a percent of the capex. The second highlight has to do, as I said, with the floater design. What you see here on your on the right, it is the floater of the 15 megawatt IEA wind turbine, which was tested in the wave tunnel, in the wave tank, not tunnel, in the wave tank in Plymouth, and defined a blind benchmarking in which 15 participants from all over the world sent results, and the comparison will be published in I believe in the next months. On the left-hand side, you see a snapshot of the simulation, where you see the floater in the middle with the mooring lines and the free surface of the simulation. In this benchmarking, we have used three-dimensional CFD using our home-developed software, MapFlow, which is a two-phase flow solver, including air and sea at the same time. On this slide, you see the results and the comparisons. The first line has to do with the comparisons of our predictions, MapFlow, with the experiment, and on the lower line are the group, let's say, comparisons of all 15 participants. You can see that the kind of accuracy we get here with respect to the free surface elevation in front of the floater, and here with respect to the pitch response of the floater are at least among the best of this group. The third highlight has to do with what I already mentioned, high fidelity modeling, which has to do with the safety of wind turbines, and it goes beyond the state of the art in the following sense. Normally, wind turbines are calculating turbulent winds, where the turbulent inflow is assumed to be frozen, and so it doesn't interact with the wind turbine. Of course, it has an impact on the behavior of the wind turbine, but not the other way around. Here, both the turbulence and the wind turbine are in one single simulation, and the wind turbine is considered as being a deformable body, so it is a fully aeroelastic simulation. What you see here is the vorticity shed by the rotor, and in front of the rotor you can see the incoming turbulent fluctuations. The modeling context for this kind of simulation is large eddy simulation modeling, which is considered today the most advanced worldwide. The benefit out of using such kind of modeling is that you can provide better prediction of the loads, and therefore you can allow a better design, and by that a reduced LCOE. What we see here is a comparison of the fatigue loads. On the left-hand side has to do with the spectrum, and on the right-hand side has to do with the ranges and the number of cycles that appear in the simulation. The two simulations you see is the AL is the one with the LES modeling, and the other one is the standard blade element momentum simulation. And you see that there is a difference which can be in one number seen here in the what we call damage equivalent load, where the one with the LES is 43 and the other one is 49. All of the results have to do with the flap-wise bending moment of the blades. So, having presented the three highlights, I've come to what is our message our message for Offshore Wind and from the Energy Competence Center. We combine our broad engineering knowledge in wind energy and maritime technologies that we inherit from the National Technical University of Athens, from the universities and the research centers. We have long research expertise at European and national level. I already mentioned that. We had conducted we have conducted 2 floating wind turbine research projects, and we can build on that. And third, validated high-fidelity computational tools and procedures beyond the state of the art. And we offer highly specialized services, high fidelity in design and analysis of floating turbines and parks, and optimized solution based on our long-lasting research expertise. Thank you very much.